Informally, we say that a function is not continuous if it has an interruption. In other words, if there are any holes, any jumps, or any gaps in the function, that function is not continuous. So let's take a look at 3 examples of functions where they are not continuous. So the first function that we want to look at, g of x, is equal to x squared minus 1 over x minus 1. So looking at the function, we can already see that at x equals 1, there's going to be issues because we're going to have a 0 in the denominator. And if you graph this function, it's actually going to be a linear function that crosses the x-axis at -1, crosses the y-axis at +1. So it looks like this. There's going to be a hole at x equals 1, and then it's going to keep going in the other direction. So we say that because the function evaluated at 1 is undefined, there is a discontinuity at the value x equals 1. Another example of a discontinuity is the function h of x equals x divided by the absolute value of x. So this is a pretty common function that we tend to see a lot. It's going to have 2 values, either 1 or -1. If the x values are positive, then it's going to look like a constant function going to the right like that. If the x values are negative, it's going to be the same thing but going in the opposite direction. And the reason why we would say that this function is undefined is because the limit as x approaches 0 from the left-hand side of f of x is not equal to the limit as x approaches 0 from the right-hand side of f of x. In other words, the limit as x approaches 0 does not exist because we see that we have different left and right behaviors. The last case that we can look at is the function f of x equals 4 minus x whenever x is not equal to 2, and 0 when x does equal 2. So it's a piecewise function. So when x is equal to 2, the function is going to be 0. Everywhere else, it's going to follow 4 minus x. And 4 minus x is a linear function that crosses the y-axis at 4, crosses the x-axis at 4, and it's a negative linear function, so it's going to go down until it reaches x equals 2. There's going to be a hole there, and then it's going to continue until it crosses x equals 4. This function is not continuous because the limit as x approaches 2 of f of x is not equal to the function evaluated at 2. And these 3 examples naturally lead us to come up with a pretty important definition of continuity that you should definitely know and memorize. So the definition of continuity is the following. We can say that a function f is continuous at a point C when the function has to be defined at C. So this has to be defined. Secondly, the limit as x approaches the value c of f of x has to exist. And then the third part is that 1 and 2 have to be equal to each other. The limit as x approaches this value c of f of x, that has to equal the function evaluated at c. So if these three conditions are met, then we can say that the function is continuous. Otherwise, the function is discontinuous. And discontinuity can come in two flavors. We can have something that's called a removable discontinuity. So if we go back to the example of the function f of x equals x squared minus 1 over x minus 1, as we saw above, that is a linear function that is undefined at x equals 1. If you're trying to find the limit of this function, so the limit as x approaches 1 in this case of g of x, notice that we can rewrite the function as x plus 1, x minus 1 over x minus 1. And then what ends up happening is that the x minus 1, which was causing us issues because we were ending up with 0 in the denominator, ends up canceling with something in the numerator. So that this limit then becomes 2. Okay, so anytime you can factor out the thing that's causing the issue, the thing that's causing our function to be having an indeterminate form, then that's an example of a removable discontinuity. And if we look at the graph again, intersect the x-axis at -1, it's going to cross the y-axis at +1. So it's going to look something like this. Once it hits 1, there's going to be a hole there, and then it's going to keep going in the other direction. If it looks like you can redefine the function, that's the term that gets thrown around. If you can redefine the function, or it looks like it's very easy to fill in that hole, then that would be an example of a removable discontinuity. An example of a non-removable discontinuity would be something like the function f of x equals 1 over x. So that function looks like this. Whenever x is positive, then the function looks like that. Whenever x is negative, then it's going to be the same thing, but in the other direction. So we say that at x equals 0, there's a non-removable discontinuity. There is no way that we can easily fill in or correct the function like above that would allow us to have a removable discontinuity. Another example of a non-removable discontinuity would be g of x equals the function 1 over x squared minus 4. And this function is going to look like this from negative infinity in the x-axis. If we go from negative infinity up until -3, we're going to have a vertical asymptote, and then after we cross -3, the function looks like this. So it comes from the bottom up until it hits or gets very close to 3 again, then it goes down, and then after it crosses and then after it crosses positive 3, then it looks like the left-hand side. So we're going to come down again. After it crosses 3, then it looks like this. Okay, so we're going to have a vertical asymptote at -3. We're going to have a vertical asymptote at 3. So in this case, g of x is discontinuous at 2 places. It's discontinuous at -3 and at +3. And it has a non-removable discontinuity because there's no easy way to redefine the function such that we can sort of avoid the discontinuity. And one of the results of dealing with continuous function is that we can combine continuous functions in the ways that we know how to combine functions, and the result is also going to be a continuous function. So if we assume that b is a real number and we verify that f and g are continuous at some point c, and the way that we verify f and g are continuous, we go back to the definition that I offered you at the beginning. We check the first condition, the second condition, and the third condition. If we pass all 3 of them, then we know the function f and g are continuous. If you multiply b times f, that product is going to be continuous. The sum or difference of f and g is also continuous. The product of f and g is continuous. And the quotient of f and g is continuous, granted that you don't have 0 in the denominator. Same thing when it comes to composition of functions. If g is continuous at some point c and f is continuous at g of c, then the composition of f of g is also going to be continuous at c.